Okay, this is the Year 10 Physics Term 2 Final Revision. The Term 2 Final is on Thursday, May 7th at 11 a.m. And the exam will cover the textbook, page 129 through 155. 129 through 155. On 155, it's only the top section, not about reflection, refraction, diffraction. Okay, so if you can remember back before the break, we were talking about electric charge on page 129. I'm just going to go through the textbook. You may want to open your textbook and kind of follow along, as I will be referring to pictures and information from the text. I've also attached in Google Classroom several videos that are very thorough in explaining the topics, and I encourage you strongly to watch those videos before the exam next Thursday. Okay, so again, I'm on page 129 in your textbook on electric charge. Essentially, electric charge is the idea that atoms are made of positively charged protons and negatively charged electrons, and the attraction or repulsion of those charges causes many of the phenomenon we see in the natural world, like balloons sticking to the ceiling or getting shocks from doorknobs, or it's the reason we don't fall through the floor. It's the reason the world behaves as it does, is this idea of electric charges, protons and electrons, and the electric fields that those charges cause. So we have conductors and insulators. Conductors are generally metals, and conductors allow electrons to flow through them easily. The atoms in the conductor are ions, meaning they have fewer electrons than we would expect, and that extra electron exists in an electron cloud. Or we can say conductors have free electrons, that when we apply a voltage or a potential difference, those electrons are able to flow freely with fairly low resistance. And we talked about with conductors, these metal conductors, the thicker the wire, the easier it is for the electrons to flow. Similar to a 12-lane traffic highway, there's lots of direction, many lanes for the cars to go. And a thick wire, we can think about there are many lanes for which the electrons to flow through. But in a thin wire, that's like a 2-lane highway or a 1-lane road, and it's very difficult for the electrons to flow. There's not as many pathways. So a thin wire has a higher resistance than a thick wire. And also a longer wire will have a higher resistance because there is more of a chance for these free electrons to collide with the atoms or the ions in the metal wire. Conversely, we have insulators. Insulators do not have free electrons. The electrons are fixed in their orbits around the atoms or the molecules of the insulator and are not able to flow freely. So if we apply a potential difference or voltage, the electrons cannot move or flow. So insulators do not allow current to flow, and conductors do allow current to flow. I would also like to say that a conductor is a conductor of electricity and heat. Essentially, they are the same thing, where an insulator is a insulator of electricity and heat. So if something is a good conductor of electricity, it is also a good conductor of heat, because heat is created by the collision of these flowing or these moving electrons colliding with atoms that we see in conductors. Okay, page 130, and here we have the diagram where we have the red spheres are the metal atoms, and then these small yellow spheres are the sea of electrons, or the electron cloud, or the free electrons. And this is a solid. We can tell by the rigid or regular arrangement of the metal atoms They're all lined up, unlike a liquid or a gas where they would be free to move around. And in a liquid, they would not be in a regular grid arrangement. So here is a picture of the solid with the free electrons. Also on page 130, we have this table, and this is a list of conductors to insulators. Starting at the top, the best conductor is silver, and then we go down. Copper is a slightly less conductive material, meaning the electrons do not flow as easily. There are more collisions. Aluminum is, again, slightly less conductive than copper, and then iron is the poorest metal conductor on this list. Then we go to graphite. Is still a conductor, but even worse than iron. And then silicon, we'll come back to silicon, and then we get into plastics. So here we're now no longer really calling these conductors, we're calling these insulators, and we start with most plastics being fairly good insulators or quite poor conductors, and then we go to oil, glass, and then finally Teflon at the bottom of the list, which is the best insulator or the worst conductor. It really locks its electrons in their orbits and does not allow any current to flow. Silicon, we see, is labeled as a semiconductor, and a semiconductor is both a conductor and an insulator. At room temperature, it is an insulator. It does not have any free electrons, and it does not allow a current to flow at room temperature. But if it is heated a little bit by applying a voltage, the atoms begin to vibrate, and as they vibrate, they release their electrons into an electron cloud, and now you have a conductor. So semiconductors are insulators at room temperature or at certain temperatures, but when a voltage is applied or when they are heated, the particles vibrate, releasing electrons into an electron cloud. Then these free electrons are able to flow and conduct electricity. Semiconductors. Germanium is the other semiconductor, silicon and germanium. Okay, next we have charging insulators by friction on page 130, and this is the idea that we can rub two insulators together and we can create a charge, or we can move electrons from one object to another. And we can only do this in insulators. You cannot charge metals by rubbing. We charge metals in a different manner, which we'll see later. So the idea is, as we rub two insulators together, the electrons from one insulator are grabbed or attracted by the atoms in the other insulator and then stuck in their orbits. So one insulator is going to lose electrons and the other is going to gain electrons. And so if we look at page 131, at the top of the page we have the diagram of an atom with protons and neutrons in the nucleus, and then these electron orbits, or the cloud of electrons. And then in figure 2.45, it says a negatively charged atom. So we look at, in figure 2.45 on page 131, we have 3 protons in the nucleus and 2 neutrons, which have no charge. So we have 3 positive charges. And then in the electron shell, we see we have 4 electrons. So we have 1 more electron than proton. Electrons carry a negative charge, so this atom, or this ion, has a negative charge. And so it's a negatively charged atom because it has 1 extra electron. Below that, in figure 4.26, we see the opposite, where we have 4 protons and 3 neutrons in the nucleus, so 4 positive charges, and in the electron shell, only 3 electrons, or 3 negative charges. So now we have 1 extra proton, so here we have a positively charged atom. Going on, page 132, we see attraction and repulsion, and in figure 2.48, on the left we see those 2 blue spheres with the negative sign inside, so those are two negative charges. And we see that like charges repel. These are both negative. They're like charges. And so the electric field lines are repelling from each other. Those lines around the two charges are not attracting to each other. They're pushing away from each other. In the middle picture with the two red spheres and the positive charge, those are still like charges, so the electric fields repel. So we see very similar field lines. And then on the far right, we have a positive charge and a negative charge, and here we see the electric field lines are attracted to each other. Opposites attract. So the electric charges are connected. If we look closely, you can see that the arrows on the electric field lines are moving from the positive charge to the negative charge. And we do say that the electric field lines move from positive to negative, or out of positive and into negative. And if we go back to the blue spheres on the left, we see that in these two negative charges, see the charges moving to the field lines moving to the negative charge, or the arrows are pointing into the blue spheres. And in the two like positive charges, the two red spheres, the field lines are moving out of or from the positive charge, from positive to negative. Page 133, at the top of the page, it has the picture of the ceiling and the charged balloon. So we have a negatively charged balloon. Someone has taken this purple balloon and rubbed it on their hair or their shirt, and through friction, the balloon has taken in or grabbed some electrons from the person's hair or whatnot. And so because the balloon has gained electrons, it has a negative charge. It has more negatively charged electrons than it had before. And also, we should point out that the hair has fewer electrons, so the hair becomes positively charged. And we see the boy below, his hair is standing up because all of his hair has a positive charge, and those are like charges, so the hair will repel from each other and give him the spiky hair. So as we bring this negatively charged balloon close to the ceiling, we see that the negative charges in the ceiling tile are pushed away from the negative charges in the balloon. So the negative charges are pushed away from the like charge in the balloon, leaving at the bottom of the ceiling, the bottommost part of the ceiling, positive charges, or these are atoms that are missing one electron. So now we have a positively charged bottom of the ceiling and a negatively charged balloon. So this balloon is attracted to the ceiling tile and it sticks to the ceiling, as we saw on the video. All right. Let's go on to page 134. And here we have the description of the gold leaf detector, So here, the first stage is we are rubbing an acetate bar with cloth. So we are charging an insulator by friction, and we see the acetate bar has a positive charge. Positive charge means it has lost electrons. As I rub the cloth onto the acetate bar, electrons are leaving the acetate bar and going to the cloth. So now the cloth has extra electrons and has a negative charge. Stage 2, I bring the positively charged acetate bar to the gold leaf detector. Because of that positive charge, the free electrons in the gold leaf detector, in the metal cap and the gold leaf and the metal rod, the free electrons are attracted to the positively charged acetate rod. So they flow up to that metal cap. And you see the metal cap has many negative charges here as they are attracted to the positive acetate rod. But at the bottom of the gold leaf detector, the gold leaf and the metal rod are positive because their electrons have left. their electrons have gone up to the metal cap to try and join with the positively charged acetate bar. In stage 3, with your finger, you touch the metal cap of the gold leaf detector. And what happens is electrons flow from your finger down to the bottom of the gold leaf detector in the gold leaf and the metal rod, and they fill those positive charges, or the electrons from your hand move to the bottom, and so now there is balance of charge in the metal rod and the gold leaf, and the gold leaf falls because there is no longer that like charge repulsion that we see in stage 2. In stage 4, I remove my finger and then the acetate rod, and it has to be in that order. I remove my finger and then the acetate rod, and I see that now the negative charges that were in the metal cap spread out evenly throughout the gold leaf detector. There are some metal charges on the cap, some on the rod, some on the gold leaf. And so we do see a repulsion between the metal rod and the gold leaf. Those two like negative charges cause the gold leaf to bend away from the metal rod, as shown. If I removed the acetate rod first, the negative charges in the metal cap would move into my hand, and the gold leaf detector would not have a charge at all. So I do have to remove my finger first and then the charged rod. At the bottom of the page, we have testing charge. So we take our charged gold leaf detector from stage 4 above, and now we bring a charged rod towards the metal cap of the gold leaf detector. In step 2, they have a charged polythene bar, and remember that polythene gets a negative charge. Polythene takes electrons from the cloth. So if I rub a polythene bar with a cloth, electrons move from the cloth to the polythene bar. The cloth has lost electrons, so it has a positive charge, and the polythene bar has gained electrons and has a negative charge. So in testing charge stage 2, I have a negatively charged polythene bar brought to the metal cap of a negatively charged electroscope, and we have like charges. So the electrons, or the negative charge in the metal cap, is going to push away from the charged polythene bar, and the only place it has to go is down. So those negative charges in the cap push down to the gold leaf and the metal rod, causing the gold leaf to bend even further from the metal rod. So we would see the gold leaf bend up even more, and this bending would depend on the charge of the polythene bar. A more charge on the polythene bar would cause the gold leaf to bend even further. And in stage 3, if I bring a positively charged acetate bar, now the negative charges in the gold leaf and the metal rod at the bottom rush up to meet the positive charges in the acetate bar, and the gold leaf falls and lies in contact with the metal rod, depending on the charge, the positive charge on the acetate bar. On page 135, we have the investigation about bringing a charged rod near flowing water. And we saw that water is a polarized molecule, meaning that one side of water has a positive charge and the other side has a negative charge. So as I bring a charged rod near the tap, the water will bend towards the charged rod. And it does not matter the charge on the rod. If it is positive or negative, the water will still always bend towards the charged rod. Why is that? Well, if I bring a positively charged rod near the water, the negative pole, or the negative side of the H2O molecule, will turn towards the charged rod and attract to it, and the negative side of the water molecule will pull towards my positively charged rod. If I use a negatively charged rod, the water molecule will turn So the positive pole of the water molecule will attract to the negative charge on my rod, and I still get attraction. I will never get repulsion. The water will not push away from the charged rod. Page 136, hazards of electrostatics. Sometimes electrostatics can be dangerous. The example here is a technician is working on some computer component, and you can see he has a blue plastic wristband that is connected to the ground. So if there is any charge in his body, it does not move to the sensitive components of the electronics. And also, if there is a charge in the electronics, it would not move to his heart, but it would move to the ground through the grounding rod connected to the blue wristband. The other example of dangers or hazards of electrostatics was in aircraft refueling. Aircraft fuel is very flammable, and if there were any sort of spark near the vapors or when the aircraft were being refueled, it could cause an explosion. So aircraft fuel trucks are grounded, and the technicians who refuel the airplane wear insulated clothing. And then we have the uses of electrostatics. The inkjet printer and photocopier are examples where where electrostatics are used in technology. I've linked a good video that explains this in detail. And if we go to page 140 and take a look at the end of topic checklist, we have common electrostatic effects are caused by having extra electrons or shortage of electrons. Electrostatic effects happen when insulators have gained or lost electrons. Friction can cause insulators to become charged. And then the facts and ideas that you should understand by studying this topic. Know that some materials are conductors and that others are insulators. Give examples of each. Describe experiments to investigate how insulating materials can be charged by friction. Understand electrostatic effects in terms of movement of electrons. Understand that materials become negatively charged overall when they gain electrons and positively charged overall when they lose electrons. Remember, protons are not moving in this process. Understand that forces of attraction occur between unlike charges and forces of repulsion occur between like charges. Explain some uses of electrostatic charges. Explain the potential dangers of electrostatic charges. Okay. Let's go on to page 151, properties of waves. Excuse me. So we talked about the two types of waves, longitudinal and transverse waves. Longitudinal waves, the vibrations are parallel to the direction of travel of the wave. So the particle motion is in the same direction as wave travel. And the example of longitudinal waves is sound. So the air particles are vibrating backwards and forwards in the same direction the sound is traveling. So those are longitudinal waves. And then we have compressions and rarefactions. Compressions are the areas where there are lots of in air and sound. Compression, there are lots of air particles bunched together, and in the rarefaction, there are few air particles in that area. And we see the compressions have a high pressure and the rarefactions have a low pressure. As the sound wave travels, these particles move back and forth. The second type of wave is a transverse wave. Transverse wave, the example is light. And in transverse waves, the vibrations are at right angles to the direction of travel of the wave. So in light or in water waves, we see that if we look at one water molecule as the waves move by, that water molecule actually is moving up and down. It is not flowing in towards the beach. The wave is moving in the direction, but the water molecule is actually moving at a right angle to the direction of wave travel. And the example is light or water waves. Next page, 152, we have two pictures of a longitudinal wave and a transverse wave. The longitudinal wave, we see he is pushing that spring towards the fixed end, and we see the spring kind of bunches up in those compressions and stretches out in the rarefactions as the wave travels. And if we were to look at one coil of the spring, we would see it's moving backwards and forwards in the same direction that the wave is traveling, towards and away from that fixed end. In the second picture, the transverse wave, he is moving the spring up and down on the table, and we see it makes this S wave, or this sine wave. So if we look at one spring, we would see that that coil of spring is not moving towards the fixed end, but it is actually moving at a right angle to the direction of the wave, or up and down. It says that in figure 3.2, longitudinal and transverse waves are made by vibrations. Both types of waves have a repeating shape or pattern. Okay, next is amplitude, frequency, wavelength, and period. So we have on the left a diagram of a transverse wave. So on the y-axis is particle motion, and on the x-axis is distance. And then we have some things labeled for us. Amplitude is the distance from resting position, that center black line, to the top of the wave or to the bottom of the wave. So that is the amplitude, the distance from the resting position to the top of the wave. Not the distance from the top to the bottom. That would be two amplitudes. Also, we're given wavelength, and we see here this wavelength is marked from crest to crest. Wavelength is distance, and usually we use meters. So the distance between the two high points, or the two crests, that is a wavelength. But you can measure wavelength from two troughs as well, or two bottom points, or from two 0 points, as long as the wave is approached in the same direction, not just the positive portion of the graph, but the positive all the way through the negative back to the 0. On the right, in longitudinal waves, we see the wavelength shown here is from a rarefraction to rarefraction. The wavelength, you could also measure the distance between compressions, and those would be the same. From where the springs are bunched together, the compression, or where they're stretched out, the rarefraction. Note that in transverse waves, we don't talk about compression or rarefraction. Only in longitudinal waves do we talk about compressions and rarefractions. So the vocabulary associated with waves, we have wavelength is the distance between two adjacent peaks or two adjacent troughs. The time period is the time taken for each complete cycle of the wave motion. So that is the time for one wave to pass a given point. Amplitude is the maximum particle displacement of the medium's vibration from the undisturbed position. If we're talking about sound, we're talking about loudness. Amplitude is loudness. And wave speed is the distance the wave travels in 1 second. And the unit of wave speed is in meters per second. And that waves transfer energy and information. The idea that waves transfer energy and information. Page 154, the relationship between speed, frequency, and wavelength. So we have the equation wave speed equals frequency times wavelength, or V, wave velocity or wave speed, equals that F is for frequency times, and that upside down Y, we say lambda, and that is wavelength. So V equals F lambda. velocity equals the frequency times the wavelength. You can check those worked examples and see how to do the math there. And then on page 155, we have the relationship between frequency and time. So frequency in hertz, the unit of frequency is hertz, is equal to 1 over the time period in seconds, or F is equal to 1 over T. Also, you can see that then T is equal to 1 over F. So if we look at this, F is equal to 1 over T, and we substitute 1 over T into our equation on page 154, V is equal to F times lambda, or velocity is equal to frequency times wavelength. Instead of saying frequency, I'm going to say 1 over T. So I have velocity is equal to 1 over time times wavelength. And so the units would be, velocity is 1 over time, that's 1 over seconds times meters. So I do see that velocity is in meters per second. You may be asked to change frequency to time period or time period to frequency. Okay, so that is all. Please take a look at your textbook, maybe reread those chapters and watch those videos, and we will take questions in class next time. Thank you very much.